I'm Paulo Carey, and this is my digital sampling lab report. So, the motivation of this lab was to investigate various properties of time and frequency domain plots of signals. Some of these properties being noise, Fourier transformations, which is turning a time domain into a frequency domain, power, and filtering of these signals. So we can use a bunch of these properties to clean up a potentially messy signal. Filters can be used to remove excess noise in regions where the main signal is insufficient. Fourier transforms can be used to figure out what sinusoidals comprise a signal, and we can use power to know how quote, strong a signal is. So moving on to a Fourier transformation here, we have over here a signal that is comprised of several sinusoidals. And what the Fourier transformation allows us to do is isolate the frequency of each individual sinusoidal that's comprising the overall signal. So it allows us to see nicely what makes up this signal. And we also get the relative power or contribution of each of these individual sinusoidals. We're used to seeing signals as a function of time. Over here is just the basic sinusoidal A sine WT plus B. Now, talking about noise, we have a really noisy signal in the time domain here. We have two types of noise. White noise is a noise that is independent of the frequency, and pink noise is noise that is more prominent in lower frequencies and kind of follows an inverse relationship. So we can use filters to help remove these noises. For example, a high-pass filter would be useful for removing pink noise, as pink noise is predominantly lower frequency. So here we have two parts, or really three parts, of the lab. The first week was validating the equipment. The second week was analyzing 11 sample tracks. And the third week was an independent experiment that I came up with on my own. And to conduct this lab, we used equipment that was given to us by the TAs, a LabJack T4, a microphone, and a 3.5 millimeter audio breakout adapter. Of course, with wiring and hooking it up to the computer and all that. So week two, here's the results of analyzing the 11 sample tracks. So most of the tracks, or all of the tracks, were comprised of either single sine waves, triangle waves, square waves, ramp waves, or a product of sines or a sine inside of a sine. So some interesting observations that I noted here was that the ramp, square, and triangle waves were all extremely noisy, and it was actually to the point where it was hard to figure out which was which. And also another interesting note was that the product of two sine waves turned into a difference of signs thanks to trig identities, which is actually in the lab notebook notes. So here we have some principal frequencies of each of these and other frequencies here. The noise kind of appears as the other random frequencies, by the way, because noise manifests itself as random, smaller power contribution frequencies outside of the principal frequencies. So week three, I decided to make my experiment about comparing the human vocal cord with computer-generated tones to kind of investigate the noise that is present in human vocal cords. And to do this, I compared four generated tones at 1000 hertz, 1200 hertz, 1400 hertz, and 2000 hertz, along with physically whistling these tones. So that way I could have a clean comparison with actual human noise. So I analyzed mainly the power spectrum plots to do this, of course. And then I removed higher frequency from the plots because nothing was really happening there, and it just allows for better scaling. So speaking of, here are the plots that were generated, and you can see that I was actually decently spot on with whistling the tone versus the computer-generated tones. And you notice that even though it's kind of zoomed out right now, there is a noticeable amount of pink noise where I have this really big spike of noise on the lower frequency region here before it kind of tapers off. Now, there is also white noise present, which I will show on the next slide when I do some zoom-ins. Also, the relative response of each of the plots are given here, and they follow the order that's mentioned up here from top left to bottom right. So here's some close-ups that I want to go over. You see here that this is a close-up of the pink noise, where this does follow that inverse relationship. You see it kind of peaks at around 0 hertz and tapers off. And here's some miscellaneous white noise here where you see the whistling is significantly bumpier than the generated tones. So in conclusion, I was able to study the noise generated from the human voice. And what I saw was that both white and pink noise are present from the human vocal cords. Now, there are a couple of shortcomings here. I recorded my audio input inside my room in my apartment, which did have a fan and also is above a road, so there could have been several extra noise sources. And also, the microphone quality wasn't the best, so I could have moved to a different place and used a better microphone to mitigate this. Um, Other notes will be in the lab notebook, so please check that PDF.